Okay, guys, welcome to day 4. So I'll start by going over some of the harder problems from yesterday's worksheet. So I'll share my document camera and just go over some of the problems there. Um, so let's begin with maybe just a couple of easier ones. Like, for example, something like number 2. So number 2, we were asked to evaluate the limit as x approaches infinity, the function 700x to the third minus 20x all over 0.2 x to the fourth. And if you remember from last time, the trick with these is really just to try to determine which terms grow the most quickly in the numerator and denominator and just eliminate all of these slower growing terms. In the numerator, it's this term which is going to grow the most quickly because it's an x to the third term. That's going to grow faster than a plain old x term. So we can basically drop the minus 20x term. This limit's basically going to be the limit as x approaches infinity of 700x to the third over 0.2 x to the fourth. And then at this point, we can do some cancellation, right? You've got 3 copies of x on the top and 4 copies of x on the bottom. So you can cancel some of those copies of x, right? 3 of these copies are going to cancel 3 copies down below, leaving us with, well, the 700 is still there, and there's just going to be 1 copy of x left over in the denominator, so 0.2x. Now, we can ask now what happens as x gets really, really large. Well, as x gets very, very big, the denominator is growing, right? Because it has an x inside of it, but the numerator is not growing. The numerator is staying the same. It's fixed at 700. And so as x gets really, really, really big, eventually, it's going to take a long time because of these coefficients, but eventually the denominator will be a lot bigger than the numerator, right? At first, the numerator is going to be much larger, right? Like when x is equal to 1, the numerator is going to be 700 and the denominator is going to be 0.2. But eventually, x is going to be a million, a billion, a trillion, and eventually the denominator will get much, much larger than the numerator. And so, when you have a fraction where the bottom is much, much bigger than the top, the overall value of that fraction is very small, right? So as x goes to infinity here, the value of this overall fraction is approaching 0. So this limit is equal to 0. Yeah, so anytime the denominator grows more quickly than the numerator, that's what you're going to get. You're going to get 0. And anytime the numerator grows more quickly than the denominator, you're going to get infinity. It's only when the top and the bottom sort of grow at a similar rate that you're going to get anything different, like 2/3 or 5/4. So let's take a look at something like, let's see, how about maybe number 8. So number 8, very similar. It's the limit as x approaches infinity of the function sine of x over negative x. Now, what's happening here? There's not really anything to cancel, right? There's only 1 term in the top. There's only 1 term down below. So there's not really any way to simplify this expression. Instead, we just have to ask ourselves, like, what's growing faster, the top or the bottom? The numerator, sine of x, remember, the sine and cosine functions don't really grow. They just kind of oscillate up and down like this. So the top is not really growing. It's always staying between positive and negative 1. And but the bottom is definitely growing, right? As x gets bigger and bigger, that denominator is going to get bigger and bigger. So this is another problem where the bottom is growing more quickly than the top. And that means that for large values of x, the denominator is going to be much bigger than the numerator. So the overall value of the fraction is going to be very small. And so this thing's going to be 0, just like the last problem, okay? Yeah, and that's true for number 9 as well. It's true for a lot of these problems, right? Okay, let's take a look at number 10. Number 10 is interesting. So if we take a look at number 10, it's the limit as x approaches infinity of cosine of 1 over x. Okay, well, what's happening? Well, x is getting much bigger, right? X is getting larger and larger. And as that happens, this fraction is getting smaller and smaller, right? It's going to be like 1 out of 10, 1 out of 100, 1 out of 1,000,000. So for very, very large values of x, this fraction here is essentially 0. It's like 1 out of 1,000,000, 1 out of 1,000,000,000, getting smaller and smaller. It's approaching 0. So this function is going to approach cosine of 0, right? Because that 1 over x is just going to get closer and closer to 0. So what is cosine of 0? If you haven't done any unit circle trigonometry, it might be kind of hard to figure this out. But certainly if you're coming from pre-calc, then you know that cosine of 0, hopefully you know that cosine of 0 is equal to 1, right? That's like, remember your unit circle? Well, I won't get into it here right now. I don't think it's time to review all of that. But let's jump ahead to something like in part 2. Let's take a look at 1a. So this is from part 2. It's very similar. It's a limit as x goes to infinity of e to the power of cosine 1 over x. So there's that expression again, cosine of 1 over x, just like in the last problem, but now it's sitting inside of an exponential. So as x gets really, really big, once again, this fraction is getting very, very small. It's going to 0. So this thing is basically going to approach e to the cosine of 0. And what is cosine of 0? It's 1. So this whole thing is basically going to be e to the 1, which is nothing more than e. Okay, so that's 1a. That's how that one goes. And b is quite similar. Let's do a tough one. Let's do 1c. Okay, this one here, it's a rather complicated function. It's the limit as x approaches infinity of 2 times the square root of x plus 10 times the third root of x over 5 times the fourth root of x minus the square root of x. And we give you a hint. We say rewrite this expression using fractional exponents. So let's go ahead and do that. Well, so let's see. So this is the limit as x goes to infinity. 2 times the square root of x, that's just 2 times x to the 1/2, right? Square root of x is nothing more than x to the 1/2. Plus 10 times the cube root of x. Well, the cube root of x is simply x to the 1/3, right? This is our exponent rules, right? Remember, just recall that x to the 1 over n is the nth root of x. You just have to remember that exponent rule. That's what I'm using here. And then at the bottom, I've got 5 times the fourth root of x. Well, that's 5x to the 1/4. And then minus square root of x, that's nothing more than x to the 1/2. Now, what's the advantage of doing this? If we write the expressions this way, then we can actually do the usual trick of sort of asking ourselves which terms grow the most quickly and which terms grow the most slowly in the top and the bottom, and eliminate the slower terms. So if I have a look in the numerator, which of these two terms is growing more quickly? Well, 1/2 is larger than 1/3. So this is the term that's growing most quickly up top. In the bottom, which term is growing more quickly? It's actually this one, because the 1/2 is larger than 1/4, right? The higher the power of x, the more quickly the term grows. So we can actually drop these slower terms. This is just the limit as x approaches infinity of 2x to the 1/2 over negative x to the 1/2. Just to be clear, this minus sign, remember, sometimes people sort of have a temptation to drop this minus sign. Remember that minus signs are really attached to the object on the right. Okay, and like I'm dropping this object here, like the 5x to the 1/4, I'm dropping that term, but the minus sign's attached to this guy, all right? So it's going to stick around. Anyway, you can do some cancellation now, right? Because you have x to the 1/2 on the top and x to the 1/2 on the bottom. You can cancel them. So that's the limit as x goes to infinity of just 2 over, well, the x of the 1/2 may disappear, but you've still got that minus sign, and that's why I've written a -1 here. So this is just 2 over -1. There's no more x to even consider, so you can sort of ignore the limit part. This is just -2. Okay, so that's how that one goes. And then maybe something like 2c from the second part, because that one's rather tricky as well. So if we have a look at 2c, we're asked to evaluate the limit as x approaches infinity of 5 times 3 to the x plus 6 times 2 to the -x over 7 times 3 to the x minus 11 times 2 to the -x. Okay, so we have to be careful here because, exponentials, like let's think for a moment. Let's just put this on hold for just a second and think about the expression 3 to the x. Ask yourself what happens to the value of this expression as x gets really big, like 3 squared, 3 to the 3rd, 3 to the 4th. This expression will get larger and larger, right? It'll get larger and larger. On the other hand, what about 2 to the -x? As x becomes larger and larger, what's happening to the value of that expression? Is it getting bigger and bigger? It feels like maybe it should, or maybe it does, but it actually doesn't. Let's just take a moment to see why. It has to do with the behavior of negative exponents. So let's imagine, what happens if you plug in a really big positive number for x here? What happens if you plug in, say, 100 for x? That would be 2 to the power of -100, right? I claim that's actually a very, very small number, not a large number. Remember what negative exponents mean. If you have a negative exponent, it really means you write 1 over and you make the exponent positive. That's what that means. So 2 to the -100 really means 1 over 2 to the power of +100. 2 to the +100 is a giant number. It's a huge number, right? It's 2 times 2 times 2 times 2. So this is 1 divided by a giant number, which means that overall, this thing is very, very small, okay? So surprisingly, as x gets very large, in the positive direction, which is what's happening here, this term gets very large, but this term actually gets very small, okay? So looking at this expression, as x gets very, very large, this term here is going to be very, very large, but this term is going to be very, very small. So you should just ignore it, right? For very large values of x, this term is going to be much, much bigger than that one. So you should just ignore the smaller term. And likewise, down below, again, you got 7 times 3 to the x. That term is getting very, very big, but this term is getting very, very small, which means that you can, after ignoring these guys here, you've got 5 times 3 to the x over 7 times 3 to the x. The 3 to the x cancels on the top and the bottom. And you're left with 5/7, which is the value of the limit. On the other hand, 2d, which is exactly the same function, but now you're looking at the limit as x approaches -infinity. Exactly the same function, but now x is going to -infinity, which simply means that x is becoming a larger and larger negative number. Now, actually, situation is reversed, right? Let's again consider what happens to this expression and this expression, but this time asking what happens as x becomes a very, very large negative number. Well, if you plug a very large negative number into this guy, you get 3, say, to the -100, which is a very, very small number, right? Because that's 1 over 3 to the +100. But if you plug negative 100 into this guy, because there's already a minus sign on the x, plugging a negative number into this expression, this minus sign is going to flip the negative back to being positive. So that would be like 2 to the opposite of negative 100, which is 2 to the just positive 100, which is very, very large. So if you think about it, as x approaches a very large negative number, this time around, these terms here are actually getting smaller. And these terms here are the ones that are getting much, much larger, bigger and bigger. And so what you should do is ignore the slower growing terms, the small terms, and only keep the terms that are very, very large. So this is going to be just 6 times 2 to the negative x over negative 11 times 2 to the negative x. Remember that negative sign is attached to this term, so it doesn't disappear when you drop this term here. The 2 to the negative x on the top and the bottom can be canceled, and that's just negative 6 over 11, which is the value of the limit. By the way, one more thing, if you were tempted to like multiply this 6 with this 2, you really shouldn't do that. Like, just, or the 5 and the 3, like just to be clear, 5 times 3 to the x is not the same thing as 15 to the x. If you want to know why that is, it's basically order of operations. I mean, by writing 15 to the x, what you're, just look at it this way. There are 2 things that are happening to this 3. The 3 is being multiplied by 5, and it's being raised to a power of x. And the question is, which of those 2 things do you do first? Do you multiply by 5, or do you raise to the x? PEMDAS, order of operations, says you apply the exponent first, and you multiply later, right? Exponents before multiplication. If you do this, then you're multiplying before the exponent, right? You're multiplying the 3 by the 5 and then raising to the x, which is the wrong order. Okay, so that's why this is not true. It's because it's violating order of operations. Okay. I'm not gonna lie, like there were a fair number of pretty significant algebraic difficulties in this worksheet. I think, particularly if you're coming into this class from Trigasis, some of these problems are pretty tough. I wouldn't worry too much about it as long as you got this general idea, and as long as you were able to get some of the easier problems, I think that you'll be in good shape. But today we're going to be doing something that is, I think, a lot less algebraically difficult. It's a lot easier. And what I'm going to be doing is I'm going to be introducing a brand new concept called instantaneous velocity, which will lead you eventually in the worksheet. You'll see something called instantaneous rate of change. And this is something that I don't think you've seen before. So the topic for today is really average velocity and instantaneous velocity. All this stuff about limits, I'm sure, you've probably wondered, like, what in the world is this all about? Like, what's the point? Today, you're going to see what the point is. I mean, there are a huge number of applications of limits, but this is the first really important one. And you're going to see it's a very basic application, something really fundamental. So I'm going to start. So here's the idea. So surprisingly, and this is not obvious, okay? This is not obvious at all, but surprisingly, there are actually 2 different kinds of velocity, right? Velocity is how fast something is going in miles per hour, or feet per second, or meters per second, or whatever. There's actually 2 different kinds of velocity. There's average velocity and instantaneous velocity. Now, average velocity is something that you've been working with for a long time. I think that you probably start learning about average velocity, maybe in elementary school or something. Instantaneous velocity is something that you probably haven't seen before in a math classroom, although you have seen it in real life. Okay, so what I'm going to do is I'm going to explain the difference between these 2 concepts. And I'm going to go over how you compute each one of them. You've previously learned how to compute this guy here, but this guy should be brand new. And in fact, it requires calculus to compute, which is why we're doing all of this. So here's the setup, okay? So here's the situation that I want you to imagine. All right, so suppose that you get into a car. All right, so you get into your car and you start driving. And let's say that in 2 hours, you go 120 miles. Okay, so like you get into your car and you drive around for two hours, and at the end of your trip, you've gone 120 miles. Okay, so here's my question: what was your velocity? Like, how fast were you going? So, what was your velocity? You might remember that, velocity is distance divided by time, right? It's how far you went divided by how much time it took. So that would be 120 miles divided by, well, the trip was 2 hours long, right? Okay, so 120 divided by 2, that would be 60. So that would be 60 miles per hour. So 60 miles per hour is how fast you went, okay? Like I said, that's not anything new. You've done that before. But here's what I want you to think about for a second, okay? Were you going 60 miles per hour during the entire trip? Like, probably not, right? I mean, like, you get into your car, you're pulling out of your parking space, right? And you're going very slow at that point. And then, you're driving around the parking lot or whatever, and that's quite slow as well. You get onto a side street, that's like 10 miles an hour or 20 miles an hour. And then finally you get onto the highway, and then maybe you're going 65 or 70 or whatever. So this number here, this 60 miles per hour, I want to be clear, this 60 miles per hour here is an average. It's how fast you were going on average, right? Most of the time, you were probably going either a little bit below 60 miles per hour or a little bit above 60 miles per hour. And the only way you get this number 60 is by averaging, okay? So this guy here, that is an example of average velocity. It's average velocity. It's not how fast you were going the entire trip, it's how fast you were going on average, okay? So if that's average velocity, then what's instantaneous velocity? Instantaneous velocity is what your speedometer says, okay? Instantaneous velocity is how fast you're going at a particular instant, at a particular single moment in time. Okay, do you see the difference between these two things? This 60 miles per hour is just your total distance divided by your total time, how fast you're going on average. But at any particular moment, your speedometer could be above 60 or it could be somewhat below 60. And so we see that, yeah, even though your average velocity might have been 60 miles per hour, your instantaneous velocity, what your speedometer was reading, was probably not 60. Right? Maybe sometimes it was 60, but probably sometimes it was above and other times it was below. So to summarize, average velocity, first of all, average velocity is something that only makes sense over an interval of time. Okay, like we computed this average velocity over a 2-hour length of time. Okay. So average velocity is a concept that applies to a span, an interval, a duration of time. So average velocity over an interval of time. That, of course, is just the total distance that you went divided by the total amount of time that it took you to go that distance. Okay, that's what we just computed here. On the other hand, instantaneous velocity. instantaneous velocity. First of all, instantaneous velocity is different from average velocity because it's not something computed over an interval of time. It's not something that's computed over a span of time, but rather it's something that is computed at a single moment in time, right? It's what your speedometer is saying right now at this very moment, okay? So instantaneous velocity is something that we measure at a moment, an instant in time, okay? It's what your speedometer reads. And the truth is that we don't have a formula for that. Like, what's the formula? How do you compute that? You've never seen it. There is kind of a formula, but it's really not what you would expect. It's not really obvious how you would compute this. It turns out it's going to involve a limit. It's going to involve a limit. And I just want to emphasize, like, this is a pretty important concept, right? Like, instantaneous velocity is a pretty important idea. And it turns out that you really can't even define it without using limits. So right away, you can see the importance of limits in a very basic everyday circumstance. Okay, so how in the world? So my goal really for today is to derive or explain the formula. Okay, it's to explain the formula for instantaneous velocity. Okay, so where does the formula come from? Let me first of all ask the following question. Let's think again about this car trip. Okay, so let's suppose that you go on this 2-hour car trip, and in 2 hours you go 120 miles. But let's think again about that car trip, and let's suppose that I want to know the instantaneous velocity at 1 second into the trip. So when you've been driving for exactly 1 second, so just 1 second into the trip, 1 second after you turned on your car or whatever, what was your instantaneous velocity at that moment? That's what I want to know. So what was your instantaneous velocity at, let's write t for time, t equals 1 second, right? So like what? How fast were you going 1 second into your trip? Okay. So let me ask you, do you think that the answer to this question is anywhere close to 60 miles an hour? I hope not, right? Probably not. Because 1 second into your trip, you're basically leaving your parking space, right? Like you're going very, very slowly. You're not going 60 miles an hour. Okay, so whatever the answer to this question is, it's definitely not 60 miles an hour. In fact, it's nowhere close. So here's what I would say. I would say that 60 miles per hour is a terrible approximation of the answer. All right, 60 miles per hour is nowhere close to the answer to this question. I hope we all agree on that, okay? 60 miles per hour is a terrible approximation of the answer. It's not a good approximation at all. But I really want to take a moment to think about why is it that 60 miles per hour is so different from the right answer. I mean, I don't know what the right answer is. Maybe it's 3 miles an hour, or maybe it's 2 miles an hour. But why is 60 like the wrong answer? Why is 60 such a bad approximation of the right number? The reason why is, if you remember, 60 miles per hour, this number, it's an average, right? It's an average that is computed based upon your entire trip. And during that entire trip, yeah, you were in the parking lot for like, maybe a couple of minutes, but most of your time you probably spent on the highway, right? And so the average velocity is getting skewed very strongly by all that time that you spent on the highway going very fast. Whereas when you first start your trip, you're going very slow. Okay, so that's why the 60 miles per hour is so off. It's because it's an average velocity, which is being computed over the entire duration of the trip. And that entire trip includes lots of time where you were on a highway. That's why it's so wrong, right? That's why the 60 miles per hour figure is so wrong. So here's an idea. What if instead of computing the average velocity over the entire 2-hour trip, okay, what if we just did the average velocity over the first 30 seconds of the trip? Okay, think about that. Suppose we did the average velocity over just the first 30 seconds of the trip. Do you think that would be closer to the right number of how fast you were going exactly 1 second in? I think it would be, right? Because if you think about it, the first 30 seconds, you're pulling out of your parking space, and then maybe you're in the parking lot. But during those first 30 seconds, you're just beginning your trip. You're probably going very slow. And so the average velocity over those first 30 seconds of your trip would probably be a much better approximation of the true number of the instantaneous velocity at 1 second. So the average velocity over just the first 30 seconds would be a better approximation, right? Remember what we're trying to approximate. We're trying to find the instantaneous velocity exactly 1 second into your trip. This would be a better approximation. It would be closer to the right number, wouldn't it? But if you think about it, it's probably not going to be exact because, in the first few seconds, 5 seconds, maybe you're leaving your parking space and you're going very slow, like 1 mile an hour or something. But then when you're in the parking lot, maybe you're going 10 miles an hour, which is faster probably than you're going 1 second in, right? And the average velocity during the first 30 seconds is probably still quite a lot faster than you were going just 1 second into the trip, right? So how could you get a better approximation? Well, what if you just computed the average velocity over the first 1.5 seconds? What if you did that? The average velocity over the first 1.5 seconds, okay? Like you look at how far you went over that interval of time, you divide by how long you spent, 1.5 seconds. That would be really close to the true instantaneous velocity 1 second in, wouldn't it? So this is the idea that I want you to see. We can use average velocity to approximate instantaneous velocity. Okay, but you have to make the interval of time quite small. Okay, like this, the average velocity over the entire trip was 60 miles an hour, and that is a terrible approximation of the instantaneous velocity 1 second in. If you consider a smaller interval of time, just the first 30 seconds, then the average velocity over that time interval is going to be a much better approximation, okay, of the instantaneous velocity at 1 second. And if you compute the average velocity over just the first 1.5 seconds, that's probably going to be really close to the true number. It's probably going to be very close to the true number. And so the big idea here that I want you to take home from from this discussion is that average velocity approximates. It approximates instantaneous velocity. And the smaller interval of time that you consider when looking at average velocity, the better the approximation. Okay? So, and the smaller the interval of time, the better the approximation. Okay? So this is really sort of what comes out of this discussion, and it's a clue about how to actually compute the instantaneous velocity. Without giving away everything, the basic idea is that you compute the average velocity, except you compute it over shorter and shorter and shorter time intervals. You basically let the time interval shrink and shrink and shrink and shrink until it becomes so small that it's practically an instant. That's the idea. What you do mathematically is you take the limit as the time interval goes to 0. Okay, that's what we'll see. But to make that a lot more concrete, I've really got to I've got to take another. I've got to use a more mathematical example with some actual numbers. So let's do an actual problem. So let's say that you have a rocket, okay, a toy rocket, and let's say that the height of this rocket above the ground is given by the following function. F of t is equal to 90 plus 64t minus 16t squared. Okay. So let's say that this function here describes the height of the rocket above the ground at any time t. Okay, so if you want to know how high off the ground this thing is after 3 seconds, then you plug in 3 for t. If you want to know how high this thing is off the ground after 5 seconds, then you plug in 5 for t. Okay, so let's say, and just to be clear, I do want to give some units for this thing. So t is in seconds. Okay, so t is going to be measured in seconds. And the output of the function, the height above the ground, I want to say is going to be measured in feet. Okay. Okay. So we've got this rocket, and we have this function which describes the position of the rocket at any time t. All right. And here's my goal. Here's my goal for this problem. And it's going to take a while, but in the process of solving this problem, we're going to derive the formula for instantaneous velocity. Okay. So my goal is I want to find the instantaneous velocity at t equals 1. So exactly 1 second into the trip, kind of like the car example that I was mentioning a second ago, exactly 1 second into the trip. I want to know how fast is the rocket going? Exactly 1 second after it's lifted off, okay? So thinking about what we saw in the car example, here's what we can do. We still don't have a formula for instantaneous velocity, but what we do know is the following. If we compute the average velocity, which we do know how to compute, right? It's just distance traveled divided by amount of time elapsed. If we compute the average velocity over an interval of time, then that average velocity will be an approximation of the instantaneous velocity, okay? And in fact, the shorter the interval of time that it is, the better the approximation. So what I'm going to do is I'm going to compute a bunch of average velocities, okay, over shorter and shorter time intervals containing 1 second. And we'll see what happens to the average velocities as we do that. So let's start with the average velocity over the time interval t equals 1 second to t equals 1.5 seconds. Okay, that's already a pretty short interval of time. Okay, 1 second to 1.5 seconds, right? That average velocity that I compute is going to be an approximation of the instantaneous velocity. So what is it? Well, of course, it's distance divided by time. Time is pretty obvious, right? If you're starting from 1 second and going to 1.5 seconds, then the amount of time elapsed is obviously half a second. But formally, what that is, it's, how do you get half a second? It's just 1.5 minus 1, right? It's like the ending time minus the beginning time. That's how you get the amount of time elapsed, okay? But what about the distance traveled? Like, what about the top? Like, how far did the rocket go during that time? Well, the thing is, we have a function which describes the position at any moment in time, right? I hope you agree that the distance traveled by the rocket over this time interval is going to be the position of the rocket at the end of the trip, that is at 1.5 seconds, minus the position of the rocket at the beginning of the trip, namely at 1 second, okay? Remember, this is going to give you the change in position, right? It's the position of the rocket after 1.5 seconds minus, so it's the height of the rocket 1.5 seconds in minus the height of the rocket 1 second in. That's going to be the change in height, right? That's how far it went during that time interval. So f evaluated at the end of the trip minus f evaluated at the beginning, that's going to give you the change in height. That's going to give you the distance traveled, okay, over that time interval. All right, so to actually evaluate f of 1.5, I've got to plug 1.5 into this function and crank out the numbers, and it's pretty tedious. I'm not going to do all of that. I've already got it written out elsewhere. I'm just going to tell you that if you actually do this, if you do 1.5, plug that into this whole thing, figure out what that is, and then take 1, plug that in, figure out what that is, and subtract them, I claim that you get 12. Okay, you're going to get 12. That's what the numerator is. And the denominator 1.5 minus 1 is, of course, 0.5. So 12 over 0.5, that's 24. And as far as the units are concerned, distance is being measured in feet and time is being measured in seconds. So the units are feet per second. Okay, so the average velocity over this interval of time is 24 feet per second. Okay, so, probably the instantaneous velocity at 1 second is like not too far off from this, because this is already a relatively short interval. But what we should do is we should shrink the interval to get a better approximation. Okay, let's shrink the interval of time to get a better approximation. So I'm going to do the next one a lot more quickly with a lot less explanation. This time, let's look at the average velocity from t equals 1, so same starting time, but I'm gonna make the ending time closer to the beginning of time. Okay, so from t equals 1 to just t equals 1.1. It's a very short interval of time. Okay, so what is the average velocity going to be? Well, the denominator, of course, is going to be 1.1 minus 1. That's the amount of time that elapsed between these two values. And the distance traveled by the rocket over that time interval is, of course, just going to be, just like last time, f evaluated at 1.1 minus f evaluated at 1. Right? That's the height at the end minus the height at the beginning. Okay. If you compute that, if you plug those numbers in and you simplify everything, I claim that you get 30.4 feet per second. Okay, which is actually quite different from this one, right? It's quite a large change. We shrunk the interval and the average velocity changed quite a lot. So I'm really not sure what the number should be, right? So if I want to know more, if I want to get a better sense of what the true instantaneous velocity is at t equals 1, what am I going to do? I'm going to shrink the interval even more. Okay, so same thing, average velocity, but now from t equals 1 to, let's make this really short. Let's make this a tiny interval of time. How about to t equals 1.01? That's 100th of a second. That is a really small interval of time. Okay, if you compute the average velocity, right, like over a time interval of 1/100th of a second, that should be a really good approximation for the instantaneous velocity at the beginning of that time interval. So, of course, that's f of 1.01 minus f of 1 over 1.01 minus 1. And if you punch all that stuff in and you crank out the answer, you get 31.84 feet per second. Okay. Do you notice that there's a lot less change between these two values and the first two values? Okay, that means that as I'm shrinking the interval, the average velocity is settling down and approaching something. What it's approaching is the true instantaneous velocity at t equals 1. Okay, so let's do one more. Let's do the average velocity, but now over a ridiculously short time interval from t equals 1 to t equals 1.001. That is a 1,000th of a second. Sorry, I can see that I went off the page there. And again, that's 1.001 minus f of 1 over 1.001 minus 1. And I claim that if you plug all that stuff in and you crank out the answer, you get 31.984 feet per second. Notice there's very little change between these two numbers, right? So notice that at first there's quite a lot of change between the average velocities, but then you can see the average velocities, as I shrink the interval more and more and more, the average velocities are not jumping all over the place, rather they're converging to a particular value. Okay, they're converging to a particular speed, and what they're converging to is the instantaneous velocity. Okay, so now here's the question. What does it look like these numbers are approaching? Right? What does it look like they're approaching? 24, 30.4, 31.84, 31.984. It's a little hard to say for sure, but I would guess they're probably approaching the number 32 feet per second. Okay, so if I had to guess, I would say that the instantaneous velocity at t equals 1 second is probably 32 feet per second. Okay. But here's the thing. This is pretty good, but there's no way to know for sure using this technique, right? Because maybe we shrink the interval a little more, and all of a sudden the next average velocity jumps to something totally different, right? Or maybe it's not converging to 32. Maybe it's converging to like 31.997. I mean, there's no way to know what these numbers are actually converging to. You can't be biased to 32 just because it's a whole number, right? Or maybe they're converging to 32.01, right? If you keep doing this forever and ever, like how do you know where it's really going to end and what number it's actually going to settle down on? So that is where the idea of a limit comes in, okay? What we really have to do is we have to take the limit as the length of time under consideration gets shorter and shorter and shorter and shorter forever. That is what we have to do, okay? And that's going to give us the instantaneous velocity, because as long as we're computing the average velocity over an actual finite interval, we're only going to get an approximation of the true value. To get the actual true value, you have to let the time interval become infinitely small. And the only way to do that is with a limit. Okay, so that is the importance of a limit. Pretty crazy idea. Okay, so how do limits like enter into this? So here's what I want you to notice. Have a look at these four expressions. Okay, these are the four expressions that we used to compute the four average velocities, right? And what I want you to know, what I want you to notice is just like how much similarity there is between these expressions. Like structurally, they all look pretty similar. Only a couple of things are changing. Like in all of them, f of 1 is right there and 1 is right there, right? F of 1, 1, f of 1, 1. The only thing that's changing is, let's see, do I have another color? Yeah, I do. Let's see. So the only thing that's changing is actually this number right here, right? And whatever that number is, that's the same number that appears right here. So all that's changing as you go from here to here to here to here is, this number's changing. And let me ask you, in what way is it changing? Right, like 1.5, 1.1, 1.01, 1.001. The number, the red numbers that I'm circling here, what number are they approaching? What number are they getting closer and closer to? I hope it's clear. They're getting closer and closer to 1. That tells us that we should be taking the limit as this number approaches 1. Okay, so the true number, the true instantaneous velocity, well, let me just put it this way, okay? Each one of these expressions can be written in the form, f of x minus f of 1 over x minus 1, right? And all that's changing in each of these expressions is the x. Right? Specifically, the x is getting closer and closer to 1, right? The closer that you make the x to 1, the smaller the interval of time. Make sure that you understand that, right? As x is getting closer and closer to 1, right? I mean, like x is really just the ending time of the interval. Do you guys see that? X is just the ending time of the interval, like 1.01 is the end of the interval. So you're just letting the end of the interval get closer and closer to the beginning. That means you're shrinking the size of the time interval. So if you want to let x get really, 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 really close to 1, closer and closer and closer to 1, infinitely close to 1. So that means you want to let the limit, you want to take the limit as x approaches 1. And this limit right here, whatever it is, that is the true instantaneous velocity, okay? Basically what it's doing is it's saying compute average velocities, but let the interval of time over which you're computing them get smaller and smaller and smaller forever. And that can only be accomplished with a limit, okay? So that's what this idea is saying. Now, what I'm gonna do is I'm actually gonna, we know how to compute limits, right? From a few days ago. So let's go ahead and actually compute this limit and see if we get 32 or if we get something else, okay? And that'll be whatever we get will be the true number, not an approximation, okay? You take the limit as x goes to 1, you get the real value. It's no longer an approximation. So, all right, so let me just copy some things. I've got, my function here. I use the variable t. It doesn't matter what variable you use. I'll recopy it using x. So it was 90, I'm just copying from here, plus 64x minus 16x squared. Okay, so that's my function. And I want to compute the limit as x approaches 1, I think we said, right? Yep, x approaches 1, f of x minus f of 1 over x minus 1. Okay, so that's what I want to compute. So let's do that. So so what is f of x? F of x is just this thing right here. It's the 90 plus 64x minus 16x squared. What is f of 1? That's a number. Let me just go ahead and compute that, right? So what is, over here, I'll just do that very quickly. What is f of 1? It's 90 plus 64 times 1 minus 16 times 1 squared, right? I'm just plugging 1 into this expression. So that's 90 plus 64 minus 16. I think that's 138. Is that right? Let me just ask my calculator really quickly. 90 plus 64 minus 16. Yeah, it's 138. Okay, so that's 138. All right. So I can replace f of 1 with 138. So, all right, so limit as x approaches 1. So we have limit as x approaches 1 of what? So f of x, which is this whole crazy expression here, the 90 plus 64x minus 16x squared, right? That's f of x. And then minus, so minus f of 1, which we just said was 138. All over x minus 1, okay? There's a little bit of simplification that can be done here because the 90 can be combined with the minus 138. Let's go ahead and do that. So 90 minus 138 is negative 48. So combining this term with that one, I have negative 48 plus 64x minus 16x squared all over x minus 1, okay? All right. Now, this is what I called an algebraic limit, right? It's a limit that we're trying to evaluate, and all we have is the formula for the function, right? Like we don't have a graph of this thing. We can't look at the limit by looking at a graph, or we could, but let's not. We want to use the formula. So how do you do that? Let's remember. So if you're trying to evaluate an algebraic limit, right? Remember, this is different from infinite limits. Not what, remember last time we were doing limits as x goes to infinity. Those are the limits where you like ask what terms grow the most quickly and so on. We're not doing that here. X is not going to infinity. X is just approaching a number. So this is like what we did 2 lessons ago, okay? The first thing that you do, remember with these, is you just try plugging the number into the expression, right? You just try plugging in 1 for x. And if you get a nice number, then that's the value of the limit. So if you try plugging 1 into this thing, negative 48 plus 64 times 1 minus 16 times 1 squared over 1 minus 1. I'll save you the trouble. I promise that if you compute this, you get 0 over 0, which is usually what you get in these problems, right? When you plug in the number, you get 0 over 0. And remember what this means. This means that you have to simplify this expression, like by maybe factoring and canceling common factors or something like that. As a matter of fact, that's exactly what has to be done here. So how can we simplify this? Well, there's definitely some factoring that can be done. One thing I would say is that there's a common factor here. Do you see these 3 coefficients? 48, 64, 16, they all have a common factor of 16. I'm going to pull out actually negative 16. Okay, from each of those 3 terms. The reason why is I want the x squared term to have a coefficient of positive 1. That's why I'm pulling out negative 16 so that the x squared has a coefficient of 1 instead of negative 1. So you pull negative 16 out of negative 48, that's 3. Pull negative 16 out of 64, that's minus 4x. Pull negative 16 out of this guy, you're left with plus x squared over x minus 1. This expression, the quadratic in parentheses, can be factored more, but the terms are kind of out of order. Like whenever we have a quadratic, we obviously prefer to like write it so that the x squared term comes first, and then the minus 4x, and then the plus 3. Okay, so how can we factor this? Well, we need a pair of numbers that multiply to 3 and add up to negative 4. So that would be negative 3 and negative 1, right? So x minus 3 times x minus 1 over x minus 1, right? Negative 3 and negative 1 add up to negative 4, and they multiply to 3. Okay, and then we have, as expected, we can cancel this x minus 1 with this x minus 1. And that leaves us with, we're just looking at the limit as x approaches 1 of negative 16 times x minus 3. Okay. So, so if you plug, so now that we've simplified our expression, now we try plugging in 1 again, right? So if I plug 1 into this thing, I get negative 16 times 1 minus 3, which is negative 16 times negative 2, which is 32, which is exactly what we thought. Okay. So this proves that the instantaneous velocity of the rocket at 1 second in is in fact exactly 32. but the only way to know for sure is by taking a limit. So that's a lot of work, and the problems that you're doing, they will not be this much work, most of them. And in fact, eventually you'll learn how to compute instantaneous velocity without using limits and instead using, well, I won't get into it. We'll get there eventually, but so look, so let me just, because what I want to do is I want to generalize, right? I told you that ultimately the goal for today was to come up with a formula for the instantaneous velocity, right? I sort of said, you know, we don't have a formula for that, and I want to give one to you. And you know, this guy right here, this limit that we computed, it's not the total formula, or it is, it's the formula, but not in full generality. This is the formula for finding the instantaneous velocity at time t equals 1, right? Remember, we wanted to find the instantaneous velocity at t equals 1. That's why you've got a 1 here and here and here. More generally, you might be interested in finding the instantaneous velocity at time 2 or 3 or 5 or whatever. So in general, what I want to do is come up with a formula for the instantaneous velocity, not at a specific time like 1, but at a general time, a time, we'll call it c. I'll just use a variable to represent any time at all, okay? But the formula for it is exactly the same thing as this, except I replace all the 1s with c's, okay? So this is the formula for instantaneous velocity at 1. The formula for instantaneous velocity at c is going to be exactly the same thing, just replace all the 1s with c's, okay? And that'll give us our formula. So this is what we've painstakingly derived. So instantaneous velocity at time, we'll just call it c, is given by, it's the limit as x approaches, let's see, well, it's not the limit as x approaches 1, because our time here is no longer 1, it's just c. So it's going to be a limit as x approaches c, f of x minus f of c all over x minus not 1, but c. Okay, that is the formula. Oops, I can see now that that was completely off the screen. Sorry about that. That was not clear to me when I was writing it, but that's the formula there. The instantaneous velocity at time c is given by this expression here. Limit as x approaches c, f of x minus f of c over x minus c. It's just the same thing we just derived, except instead of the specific time 1, it's a general time c, okay? So, you know, I mean, yeah, so if you want to know what is the instantaneous velocity at time 3, then you would replace c with 3 in this formula. If you wanted to know what's the instantaneous velocity at time 12, you would replace c with 12 in this formula, okay? All throughout, so here, here, and here. Right, so the exercises will guide you through this a little bit. Make sure you check your answers on some of the earlier exercises. There's like a full written out, you know, solution there so that you can, you know, really see all the steps. Also, you know, like usual, the whole beginning of the worksheet is actually like a full set of class notes. So you can sort of like read a typed up version of everything that I just went through. But okay, so yeah, okay, so that's all for today, and I will see you guys next time.